the Stapleton Trust, which together with BSAS and the European Federation of Animal Science, EAAP, PLF Commission, the three of us who have co-organized this webinar on PLF and sensing technologies in extensive systems. I'd like to welcome you all to this webinar. I hope you enjoy it. Please make sure that you've turned on the chat so that you can ask questions and look at all the other questions. And to re-emphasize what Sally has just said, if you could mute and turn off your video if you're not presenting. Now, the chair of this session is Ilan Alakmi. Ilan is head of the Laboratory for Precision Livestock Farming, PLF, at the Volcani Center in Israel. And he's also president of EAAP's PLF Study Commission. So over to you, Ilan.
Thank you, Cled. And thank you, Maggie and Sally, all the British Society of Animal Science organizer who actually make it happen. Especially Cled to recognize this trend. But before I continue, I shouldn't forget, Sally or Maggie asked me to mention the conference on April, the BSAS conference in April, the challenge of change. And to recognize a trend when it's actually happening, it is a challenge. And PLF is interdisciplinary field that starts from engineering point of view and spread to animal welfare, animal genetics, farm logistics, actually along the entire livestock value chain, intensive and also extensive systems. And I think it was Cled, so I thanks Cled to recognize this trend and said, okay, now we should make some conference, some meeting about it. And this is why this meeting happening today. The idea here today is to cover more the theoretical issues about the difference between PLF intensive and expensive system along different countries. We have a presenter from Australia, Africa, America, the US, Europe, and Israel. And 2 days from now, on the 19th, we will address more commercial and practical issue. And now is the more the theoretical issue about the PLF from intensive to extensive system. So enjoy the webinar, and I'm happy to introduce Paul Greenwood. I met Paul a few weeks ago in the ASAS, the American Society of Animal Science, and I was impressed by his activity. He is a senior research scientist in Australia and adjunct professor in the University of New England in Armadale. Paul trained in Sydney University and Cornell University. He leads collaborative research on grazing efficiency and has worked for many years on regulation of growth and development in ruminants in Australia, smart farming in Australia. Regarding the chat, please, if you have some questions, some issues, some ideas, some complaint, just put it on the chat. And at the end of each lecture, each presentation, I will select one or two very interesting questions to be answered immediately after the lecture, and all the others will be answered at a discussion at the end of the webinar. So if you have something interesting, just put it on the chat. And from this, I will select some of the questions now and some of the questions later on. Paul, the floor is yours. Good luck.
Farming for extensive grazing systems in Australia. In this talk, I'll briefly introduce the topic, provide some examples of animal monitoring for livestock and extensive systems, talk about pasture assessment and grazing management, and conclude by briefly discussing connectivity and linking data on farm and across the product value chain. It's well recognised that smart farming and extensive livestock systems will improve monitoring and objective measurement of livestock, enable better livestock control and monitoring of health and welfare, enable genetic improvement of livestock, and also improve pasture, grazing and nutritional management, and in a broader sense, landscape and environmental management. It will improve labour efficiency and management using decision support tools or DSTs, and overall it will result in improvements in productivity, efficiency, economics and sustainability. However, it does need to be noted up front that technological developments for remote monitoring and management in extensive grazing systems have varied in their success and remain limited in application and uptake. So firstly, I'll provide an example of an application of animal monitoring in extensive systems, which is walkover weighing and auto drafting. And these are a couple of examples of walkover weigh systems that are in use in Australia, the top one being an in-house system developed by CSIRO in Northern Australia in Townsville. The bottom one being a commercially available system that we use in Armidale in more southern Australia in our research. And these systems being solar powered and having 4G network communications. And they're embedded within production systems, and they include an attractant such as water and or a lick, so that when an animal comes into the system to consume water, for example, it goes through the walkover weighing unit. And there's an increasing number of these available commercially. So some of the applications of walkover weighing that are either in use or in development include automated in-field live weight measurement, drafting, estimation of parturition date, maternal parentage, postpartum estrus, also the welfare status of the animals, and also provision of supplementary nutrients and monitoring of the growth responses to supplements and other management practices. So this is an early example of work published by Luciano Gonzalez and his colleagues from CSIRO on the use of walkover weighing to track live weight and live weight change of individuals with changes in pasture availability and supplementation. And so we can see with the solid line, which tracks live weight, and the dotted line, which tracks change in live weight, as animals undergo changes in pasture availability, particularly at the end of this period, when they move into bigger paddocks with more feed on offer and then receive supplements, we can get really quite detailed tracking of the performance of the animals. The second example of animal monitoring in extensive systems is GPS tracking and behaviour measurement, recognising there are many groups working in this area and many devices that are becoming available. My colleague Robin Dobos from New South Wales DPI and others based in Armidale with the UNE Precision Ag Research Group have looked at behaviour of sheep, ewes prior to, at lambing, and also after lambing, which is a very important issue because we can suffer very substantial lamb losses in Australia. And so we can see from this first slide the location of the ewes within a paddock 7 days before lambing, the location of the ewes at lambing, and then the location of the ewes 7 days after lambing. And this type of work and the information it generates enables a much better understanding of lambing behaviours and also how to match this with environmental and management needs to reduce lamb losses. This example, again from Luciano Gonzalez and his CSIRO colleagues in Northern Australia, shows GPS tracking of livestock movements in the left-hand figure here, coupled with classification of behaviours such as grazing and then also ruminating using collar devices. And this type of information allows a better understanding of where pasture is being utilised, by what animals, and what practices are needed to improve pasture utilisation and grazing systems efficiency. Briefly, I'd like to talk about our own R&D. And a colleague of ours, Greg Bishop Hurley from CSIRO Brisbane, has developed the eGrazer livestock monitoring collar, which we use for experimental purposes to monitor location and behaviours in longer-term studies for extensive grazing and foraging systems. And so the features of this device include solar power and battery storage, two-way radio communications and capacity for real-time data recovery, and a whole range of sensors, which include GPS, accelerometer, magnetometer, gyroscope, ultrasound or audible audio, and temperature and pressure. We've conducted many studies, have others in Northern Australia, using these devices, and the progress we've made to date using high-frequency GPS and inertial measurement unit, particularly accelerometers. We've been able to deploy these on up to 40 head with up to 4 months continuous deployment. We have the capacity for on-device behaviour classification of up to 6 devices, coupled with wireless transmission from remote sites. And we use this data to develop and validate new devices, behaviours and applications, including pasture intake. So we couple these devices with a highly automated system for behaviour annotation of GPS, time-stamped data, which we use in machine learning processes to classify behaviours with high reliability. And so this is an example of recent work from a colleague, Reza Arabloui from CSIRO Data 61, working with our group using eGrazer collars. And it shows concurrent classification of six behaviours for an individual, both within a day on the left here and over a 4-week period. And this enables us to obtain very detailed behaviour data on, in our experiments, up to 40 individuals, as I said, for periods ranging up to 4 months. And this really provides the platform coupled, I suppose, the devices coupled with the behaviour classification algorithms that's laid the platform for our work to develop and validate new devices, applications and behaviours. So the final example of animal monitoring in extensive systems, which I'll only cover very briefly, given this will be talked about later in more detail by another speaker, is virtual fencing. CSIRO originally developed virtual fencing, and our colleague Dana Campbell in Armidale with CSIRO has been undertaking R&D using GPS-enabled collars and a mobile app to fence, move or monitor livestock. And so this example shows the distribution of cattle prior to deployment of the virtual fence, when the virtual fence is activated, and when the virtual fence is deactivated. And it very clearly shows the capacity of the virtual fence in this middle figure to constrain or control the movement of livestock within a specific area. And Dana and her colleagues have published widely on this, and if people are particularly interested, I suggest following it up with Dana. Also Adjusons, who have licensed the technology from CSIRO. Moving on to pasture assessment and grazing management. Again, I see Mark Trotter will talk about sensing using satellites during this symposium, and Mark has a great deal more expertise than I have in this area. But briefly, in relation to pasture assessment using satellites, the more cost-effective satellite platforms such as Landsat that have been used to date really provide guidance for pasture management, but they do this at lower resolution and frequency than some of the newer satellite-based systems, including the European Sentinel satellites, which may overcome many of the shortcomings of the existing Landsat satellites. And so in this slide, we can see the range of spectral bands covered by the WorldView 2 satellite across both the visible and near infrared spectra. And this is highly useful for the wide array of imagery and vegetation indices being developed to estimate pasture biomass availability and quality. Similarly, at the producer level, unmanned aerial vehicles have a great deal of potential to address some of the shortfalls in satellite imageries, and they have the capacity to provide quite cheap, non-destructive, high-resolution pasture and other assessments for farmers. And there's a range of sensor types that can be deployed to assess pasture availability and quality. To conclude this section of my talk, this is an example of how satellite imagery can be incorporated into a grazing management tool that's in development for farmers. My colleagues from DPI, New South Wales DPI, like Warwick Badgery and Igor Kadowski, have been developing a grazing app to help producers make more accurate grazing decisions by determining and predicting pasture characteristics and also livestock performance into the future. And they've been using machine learning for estimating pasture and livestock performance for individual paddock and farms, and very large data sets on pasture, dry matter availability and livestock performance, which they've combined with a very large amount of Sentinel satellite imagery data, climatic data, and farmer inputs to predict animal performance. And they've also developed an interface to display individual farm data and enable grazing decisions within the grazing app using real-time information. So finally, to conclude this talk, it's worth noting that in Australia we have a very wide range of extensive production systems, and hence we need reliable connectivity through wireless communications to enable application of sensor technologies. So the wireless networks highlighted in the box here, such as wide area networks, including LoRaWAN, cellular and mobile networks, and also the global area networks, are of particular interest to our extensive grazing livestock industries, and I see will be covered again in more detail by Mark Trotter. Another aspect of connectivity is the capacity to link data across different aspects of on-farm production from animals, including their performance, their location behaviour, soil, pasture, growth, and also quality of pastures, connectivity and interpretation of data, and also the use of real-time information for decision-making through DSTs. And finally, it also needs to be recognised that extensive livestock farming fits within the product value chain, and there's a great need for data collected on farm and across the value chain to be improved and integrated to enhance efficiencies and returns for individuals and organisations across the entire product value chain. And so from the perspective of the producer, smart farming for extensive grazing systems in Australia will only enhance efforts to achieve this lofty goal. So I'd like to thank you, and that concludes my presentation.
Thank you, Paul. Very interesting talk. There are quite a few questions. All of them are interesting. I would like the question of Mark Rutter. So sorry, Jean, Mark, you will wait to the end of the webinar to the final discussion chapter. The question was, how well does the e-grazer estimate dry matter intake? How is the intake estimated? Question from Mark Rutter.
All right. So just as a little background, we have a facility that we've developed at the CSIRO site in Armidale, where we specifically have set up methods to allow us to generate estimates of pasture intake with individuals or groups of animals using markers or biomass disappearance. And so we link sensor deployments to these. I suppose what we've started is at a level which is a broader level, given that we've got to have things that are practical in more extensive environments. So, we're associating, time spent within specific behaviours, specifically grazing, to estimates of intake. In our studies, which have ranged from, I suppose, monocultures of temperate grass species under very controlled conditions through to studies under drought feeding conditions, we've been able to explain up to about 60% of intake as measured by, I suppose, biomass disappearance or markers using time spent grazing. We can currently work on, I suppose, bite frequency, bite size data, but we've started at that higher level and we continue to work down through other aspects that relate to the amount of pasture that animals are eating.
I see. There are quite a few questions arrived now, but we will keep them to make the last discussion interesting. I will move now to Claire Morgan Davis. Claire Morgan Davis is originally from France. She has been in Scotland for more than 20 years. She's a livestock system scientist working in the rural highlands of Scotland. For more personal aspect, I may say that I helped, mainly Jean-Marc, I helped to convince her to apply for 2 EU projects on PLF in extensive system, and both were accepted. So she is very busy now. She is the coordinator of 2 recently granted EU projects, PLF on small ruminants, take care and smart, where we work together. Claire, the floor is you. You should open the microphone and also the camera. I don't see you. Oh, now I see you.
Livestock Farming and Sensing Technology in Extensive Grassland System webinar. Tonight, I'm going to talk to you about precision livestock farming in extensive grassland system in Europe. My name is Claire Morgan Davis. I'm a researcher at Scotland Rural College in Scotland. So an outline of what I'm going to talk about tonight. I'm going to explain a little bit what the extensive grassland systems are in Europe, a little overview. Then we'll go on to talk about the PLF, precision livestock farming, and then really the state of the art. So what sorts of initiative already exist? And I'm going to show you a little sample of what's out there, and then briefly touch on the future issues. So where are the extensive grassland systems in Europe? Well, you've got on this map, the map of permanent grassland as a fraction of total agricultural land areas. And you can see the area in dark green are where we have most of the permanent grassland, and they tend to be at the fringe of Europe. Now, if we remember that map and then compare it with the less favored area map, which is the map on the left, you can see that there is the area which are very dark brown and orange, and they are the area that are very challenged in terms of social, environmental, and climatic issues and topographic issues. And they tend to coincide with where the permanent grasslands area are already. Similarly, in the same areas, we notice that the precipitation and the climate is also quite extreme, with a lot of precipitation in these areas of extensive grassland system. Now, again, to go back to that map I was showing you at the start, you can see that if we superimpose this map of permanent grassland with the map of where the high nature value area are in Europe, there is definitely a match. So these permanent grassland area or extensive areas are very often in less favored areas, so challenged area, but they're also very important in terms of biodiversity. So they play an important role in terms of social and also ecosystem services and biodiversity. So what sort of production type do we find in these areas? Well, if we go again, the percentage of livestock in Europe, more than half are sheep and cattle and goats, but a third of them are really goats and sheep. And in these areas, we tend to find the majority of the sheep and goats, but also some cows, some hardy breeds, some cattle, as you can see on the pictures. So there is quite a variation and a very tight diversity of type of production. And also, depending on the geographical location, we have a meat production orientated livestock, or we tend to also have milk production with a cheese production. And some areas are also dual production. We tend to find the meat production more in the north and west of Europe, while the milk and cheese production tends to be more in the south and more Mediterranean base. So if we think of the challenge that this area faced, and I've already alluded to the climate, for example, so these areas are remotely based, and they have a very harsh environment, whether it's too hot or too cold. and that leads to survival issues, which also mean that in terms of welfare, there are some issues in this system. These systems are also very diverse, as I was alluded to in the previous slides, and the sector tends to be less organized. It's also a more traditional and quite aging sector, and that suffers a lot from the lack of labor, going back to the problem of the LFAs. This system tends to have a low productivity and not very efficient, and that leads in turn to quite low level of income. And finally, often there are conflicts between the farming production, tourism and environment, seeing that these permanent grassland and extensive grassland are based in high nature value areas too. So how could PLF help with these challenges? Just as a little reminder about the PLF, if we go and think about the animal here, so some biological parameter will be recorded and all the information about the environment will be recorded on sensor. Then this data will be going to model and data analysis to produce a report that can be on a computer, a smartphone, and goes back to the farmer. And then the farmer can anticipate or decide to act and say it gets a warning system. Also, we can have this data going into piloting and informing automated systems that in turn can have some automated action. So in a nutshell, that's what precision livestock farming is about. But how does that apply to a more extensive system? So if we think of the challenge I was mentioning earlier, then I was looking at the different tool we've got and what kind of tool could do. So we could have PLF tool for monitoring because the area are remotely based or harsh environment, or can have a low productivity, or even you can have conflict. So we could use PLF for that. We could also use PLF to send alert or warning system, as I was explaining a bit earlier, and that would alleviate the issues of the harsh environment, the problem of welfare, or even the conflict between the different land use. We could also use PLF to produce common protocol for collecting or monitoring data or giving data directly to inform the farmer and benchmarking. And that would help towards the problem of diversity of system and the sector being perhaps less organized. We could also use a PLF as efficiency gain and time saving, given that the technology is there for that. And that would help for the sector being less organized, the lack of labor, and the low level of income. And finally, these sorts of PLF could spark the interest of the younger generation, so that could alleviate the problem of the aging sector, but also can provide sometimes a better life and work balance, and that might alleviate the problem of lack of labor and replacement of older farmer and renewal of younger generation. And also the low level of income could be helped by having a diversification option. If you've got a better life-work balance, then you've got more time to do something else. So there are potential for using PLF tools to answer the challenge in these extensive grassland systems. Now, what are the recent PLF initiatives that have been in this sector? So what's the state of the art I was talking about earlier? Well, in 2004, we had the legislation on EID, and all animals needed to have an electronic identification tag and be individually identified. We've got two main types of RFID. So radio frequency identification, either the tags with a fixed or a mobile reader, but more and more the wearable are getting quite popular, so such as collars or sensor in or on the animal. So when I was looking at what's happening in the extensive grassland system in Europe, I could categorize 5 types of initiatives for PLF that are actually happening. One around feed and water intake and growth monitoring. The second one around grazing behavior, the third around fencing, and the fourth around health and disease management, and finally the last one on social behavior. So first of all, if we think of the outdoor weight monitoring, so there's been some development done around the walkover weight, which I know is an Australian system at the start, but I'm sure it will be covered in the later talk. But the French team down in Montpellier at the INRA have modified the walkover way to slow down the animal going through the crate and enable to calculate how much intake they've got when they come in and out of the crate. They've tested that indoors, as you can see on the picture, but also outdoors on the field and even when it was snowing, and it worked. So that's quite an interesting new system for monitoring the weight of your animal. And so the French at the Institut de l'Élevage in France have got this new project called Autop 3D, and they use a walkover way and linked with some sensors or camera to look at the body condition score of the animal, and they are trying to see if we can have a mixture of the weight and body condition score to predict the growth of the animal. The second initiative I could think of was the grazing behavior, which is really around an efficient pastoral resource management. Some work has been done 10 years ago on our research farm in Scotland, and my colleague managed to, using GPS collar on sheep, to classify the behavior between active and inactive, so between resting and grazing. And based on that, we could monitor where they were grazing in which part of the farm used on the GPS. And more recently, the Institut de l'Élevage in the south of France with the Clochette project have done something similar with a slightly different color, but again, trying to look at the different activity and classification of behavior at grazing to inform the farmer. The Italian in Sardinia have also developed a system where they've got a system around the sheep and it can calculate the bite rate and also say where the animal is grazing. And based around that, trying to inform how about nutrition and where the animal is grazing. And finally, on our research farm, we were using GPS collars to look at where the animal were grazing on different type. And again, you can see which type of vegetation they were spending most time in. So again, to inform about grazing choice and grazing behavior. The third developmental initiative is really around the virtual fencing. Because in this large area extensive grassland system, you very often don't have any fence because it's too big. So how can you know where your animal are? So the Norwegian have developed that system called no fence, and the animal work with a collar, and then they can be contained in an area as defined by the farmer. It works very well for goats, and it's being developed for cattle and sheep now. Then disease and health management. Again, Norwegian colleagues have developed a sensor, a temperature sensor under the skin of the animal, and based in conjunction with some GPS collar, they were able to have a model for detecting disease, in that case, the tick-borne fever, based around the fluctuation in temperature of the animal and based also where they were. And finally, the social behavior. So we've got research done on social network and sentinel animal in France. And again, trying to identify which animal is the most likely to be the leader in a group. And again, if you can use this as sentinel, that can be useful to inform you. And also in Scotland, we've done some work around pedigree matchmaker with collars, trying to mother the lamb with the ewe to avoid mismothering. And again, this proximity logger worked quite well, as you can see on these maps, on these graphs. So to conclude, there is a range of research and application that exists. The list I've given you is not exhaustive. Some are already available on the market, some are still research prototype, and we've got very recent project that will dwell a little bit more into these issues. So PLF can make a difference in extensive grassland system in Europe, but there is still some needs that need to be addressed. The acceptability of the technology, the economic relevance, the affordability, is it too expensive? And is the industry really engaged in developing in these areas? And also, in the bottom line, we need to have something that's cheap and small to appeal to the extensive grassland system. Thank you very much.
Wow, we have so many questions. We need a little to extend the time of this.
Only one, Ilan, only one.
Only one. No, actually, I think we will have more because we have 10 minutes. Since there are so many questions, I will start with my question. The body conditioning of scoring based on camera, the one that you presented at the beginning, how accurate it is?
I think the French colleagues are still trying to calibrate it. So it's not quite finished, but I think that one of the main issues they would have would be the problem of the fleece on the sheep, but because they use it on lamb that have been shown as where we could not really see very well on the picture, it seems to be okay compared to previous trials that they've done before, that other teams have done before. But as I say, it's work in progress, so I can't really tell you more about it.
We have about the same project. It will be nice to share the technology or data, that we will not have to reinvent the wheel in the two countries. We have identity project. I will start with the question from Racheli Gavrieli from Israel. Does the walk-through weight need herding? It obviously need herding, but what is your experience with the herding? Does it a disadvantage or advantage? How you deal with the herding to bring the animal to specific place? Voluntarily or attract by feed? This is actually also a question for Eliel.
Yeah, so I can answer for Eliel, and if he wants to butt in, just by all means. But what they've done is when they were inside, they used some pellets, but when they were outside, they were putting hay or water depending on the season. During the winter, as we could see on one of the picture, was when it was snowing, they put some feed to attract the animal in that little enclosure. But in the summer, they would use water to attract them. So I think it's really up to what the best system would work in your country to attract them. But yeah, there was definitely something to attract the animal inside that little enclosure.
Yeah, there is an issue about it.
Yeah.
Martin asked to share article. You can read exactly what he asked, so please send to him. And if there are no more questions, I think if the organizers agree, we can go forward in time. Then we will have more time for questions later on. Yeah, the other question, I think, replied by the others, especially on Laura. Okay, so we will move.
Thank you, Ilan.
Thank you, Claire. Very impressive, as usual. And see you in the project. We will move now to Professor Andrew Dowsey. Please pronounce your name. I hope I didn't make a mistake. He is a chair of Population Health Data Science at the University of Bristol and the Alan Turing Institute for Data Science and the Artificial Intelligence. He works on data infrastructure and artificial intelligence in agri-tech, health, and biomedical research. When we designed this session, I was very happy to get someone about data science because PLF acquired a lot of data. So I'm very happy you are with us. Andrew, the floor is yours.
Thank you, Ilan. Andrew Dowsey, great pronunciation. To take up a position in applied data science joined between the medical and veterinary schools. I have worked extensively on problems in human health across several sensing and imaging modalities. And in Bristol, with the help of my colleagues in Bristol Veterinary School, I have developed now a new strand in animal biometrics. My talk will be about the challenges and opportunities for AI platforms for monitoring ruminant health, particularly for grazing platforms and including resource-poor settings in lower and middle-income countries. This is motivated by the need to deliver sustainable livestock production to where it is needed on our planet. Sensing and AI will help not only to optimize day-to-day farm management and production towards this goal, but it will also underpin the veterinary and agri research that will help overcome these major challenges for livestock. As part of this, we are working with the Global Farm Platform, a network of 24 international institutes across 15 plus instrumented farm platforms. This collaboration provides a unique combination of research and practice for diverse ruminant production systems, and that's across several socioeconomic and climatic zones. Smallholder farming is underrepresented in the farm platform, something that we are looking to address through collaborations both with farm cooperatives and a new research collaboration with Strathmore University Nairobi's African Data Cube. So on to the AI. In recent years, a substantial number of automated health and welfare monitoring advancements have been presented, and these are based primarily on established wearable technologies, including GPS and accelerometers. For example, Dunn and colleagues at CSIRO, amongst others, have looked at interpreting positional data from GPS for behavior classification and for understanding field use. Jasmeet Kaler's group at Nottingham have co-developed accelerometers for sheep that with machine learning can classify behavior firstly into standing periods, walking and lying, and then on from that to whether the animal themselves is lame or not lame. GPS and accelerometry are on the whole complementary, but they have different strengths and weaknesses. GPS is probably the biggest power drain on a typical wearable, and you are then left with a choice of replacing the battery regularly, which makes waterproofing difficult, or sampling infrequently and hence losing detailed movements. Accelerometry has its own difficulties that I'll come on to. There is also the issue of getting data off the wearable, a challenge in extensive farming scenarios. Recently, this has been demonstrated using low energy technologies such as LoRaWAN. This allows the wearable to transmit data in real time to base stations that could be a kilometre or more away by line of sight. More advanced uses of this technology even allow data to hop from device to device before reaching the base station. This improves range and gets around some objects. Interestingly, as the devices capture signal strength to their neighbours, they can also be able to use to gain an understanding of relative positioning to other cows and animals, and also to static points of interest, such as drinking troughs and feed bins. This, you could say, is a poor man's GPS, but with substantially less power drain. A further option for monitoring is good old-fashioned video, including thermography and other imaging devices too. AI and particularly deep learning methods are well advanced for applying to health and welfare prediction on images and video. Using them in extensive scenarios is a challenge, however. One option is to mount the camera on a drone, something that is quite popular in crop agriculture. Apart from limited flight times and the issues of high winds and rain, there is also a need to ensure that the drones do not bother or spook the animals. To illustrate the challenges and opportunities for AI in this field, I'll just demonstrate on a couple of research projects we've been conducting. My collaborator, Jan van Weyck, from the University of Pretoria, has a significant amount of data from an accelerometer system that he's built, mounted on goats and sheep in rural South Africa. The AccuTrack system that we're using comprises an accelerometer tag for each animal, and this communicates to a solar-powered base station that then uploads the data to the cloud via the mobile network. The bandwidth needed is not high, and Africa is very well served for basic GPRS networking that's needed in these scenarios. And while this AccuTrack system wasn't designed for livestock, it's worked quite well for it. We have over a year of data, but here I show 3 days worth, where each row represents the activity of a single animal across the 3 days. This activity is given from the accelerometer simply as a number of counts per minute that the accelerometer goes above 2G, similar in style to a pedometer. I've sorted the animals by total activity so you can see the patterns better. You can see, therefore, that the animals start their activities relatively early in the morning at 7:30 a.m. And then pick it up again later in the afternoon. However, you can also see that there are a number of challenges to this data. This salmon pink color here is actually representing missing data. The wearables don't have a memory, so to speak. So if the animal is out of sight of the base station, their readings are lost. And for 3 hours at this point, the data from the whole herd was lost for some reason. You also note that some animals were not transmitting at all. And something that also AI should pick up is that some animals were transmitting but didn't have any usable activity data. The conclusion is that real life in the field data is messy. Some of these problems are being tackled by new startups such as Kral, who have advanced new devices. However, more advanced hardware comes at higher capital cost, whereas artificial intelligence doesn't have that much of a capital cost. From looking at this data, I wouldn't recommend this particular system if you wanted to detect a specific activity from a specific animal at a specific time. But if you're actually looking for some acute change in activity or more chronic dynamic changes in activity, such for a chronic disease, then I think this data is extremely rich for that. In our study, we're looking at using this system. We've been looking at using this system for matcher evaluation or automated matcher evaluation. That is seeing if the activity data correlates well to increase in anemia that's indicative of helminth infection load. Now I'm going to turn my attention to the use of video, thermography, and 3D depth imagery. These are always going to pick up more data, more interesting things about the animals than GPS and accelerometry, such as body condition, gait, complex behaviors, and also interactions between the animals. But the data rate is much bigger and therefore the task more complex. To track individuals, however, you also need at first to identify individuals, whether through natural or artificial patterns on their coats. You could do it fusing information from GPS and wearables too, but that isn't particularly easy either. Also, only about half the animals in the world do have distinctive coat patterns, so the ultimate goal would be to identify based on depth alone. We have presented a deep learning technique recently that can individually identify the 185 cattle in our herd, each with a single photo. A recent startup called Cattle Eye suggests that they do similar. But because their technique isn't published, I couldn't tell you about their accuracy or the details of their work. As our approach learns the space of all coat patterns, also as cattle are introduced into the herd, they'll be able to be identified individually with no retraining of our system. Interestingly, of course, we get very high accuracy just with video, but interestingly, we get 62% accuracy with depth alone. Now, this isn't amazingly good by itself, but it does suggest that fused with complementary information and perhaps trained to understand changes in body composition of an animal over time, we may be able to get in close to reliable identification of non-Friesians and perhaps then other species. So finally, I want to finish by discussing the fact that artificial intelligence is just as much about the social science and data governance aspects than it is about the technology itself. How do we interact, or do we avoid interaction with AI? And hence, how does it affect our individual behaviors in the future, as well as the consequences to society, in part or as a whole? The first question then, if a PLF provider sells a system to a farmer, who owns the resulting data, and what can each party do with it? Will it be available in future for say, satisfying government regulations, or for surveillance, or for research purposes, which is acceptable under GDPR? Can companies integrate data from all their clients to help the predictability for just one? How much is acceptable? What if some automated algorithm does this and finds significant outlier that is a strong evidence of malpractice? And finally, what exactly do we mean by this data? Very few companies will give you access to the raw data from their sensors. This is greatly problematic for AI and deep learning research, as we usually get far better results by applying it to raw data. In human health and genomics, there's some very...
Thank you, the organizers. Thank you, Andrew.
No, thank you.
Interesting talk. There is one question, actually two. One from where I wrote it, from Alistair Scott. I hope I pronounced the name correctly. What is the future of potential use of data from PLF behind the farm? Carbon offspring, food safety and quality, policy, biodiversity, and I will continue it to the veterinary services, the feed centers are actually along the value chain. How do you see the data flow and the benefit from it? This is one question. If we have time, we'll have another one.
Yeah, no, I think that's a great question. And I think there is absolutely fantastic use of this data, potential uses of this data when integrated together for public health, epidemiology, and all the things that you're stating. Just like potentially what Google and Facebook do by integrating and aggregating data across all of their clients. So the challenge really is, can we define a system or the regulation so that this is possible? How do we work with the companies involved or the individuals in order to get research use for the data, to bring it all together to do this? And I suppose it's not just research use, it's from some of those things you're stating perhaps from a regulatory level as well. Do we need to have government and work with policy makers in order to enable this to happen?
Yes. There is a good point from Sarah Morgan, but I think it will be very technical, so I will go to more conceptual question. From your experience from Africa and other countries, how do you see the difference in the data issues comparing to the different system, comparing to Africa, Australia, Europe, etc.? Can we take the advantage of having it one country and apply it to another country, or we have to do it on site?
Yes, that's quite a tricky question. I mean, we're still dealing with research data. Once we understand a bit more market penetration by companies in Africa and LMIC countries, we'll understand the issues a bit better. Essentially the infrastructure there, the infrastructure in Africa for getting this data with and merging it with LoRaWAN-based techniques, these kinds of things, it's all possible. You are, and I think that it's really the same technologies, because they all need to be robust, but there'll be more challenges on making them robust, perhaps in more rural or resource poor areas. And I think one issue is also the cost as well, especially maintenance costs. That might lead you to needing lower, cheaper, potentially lower quality sensors. They still need to be robust. But I think at that point, then it puts even more onus on the artificial intelligence side to make up for that. And I think it can.
I see. If you will be able to answer shortly, I will refer to the question of Mark Rutter. What is the main barrier to improving data integration? It's actually along the value chain, what we talked before, if we are getting the full value through the supply chain.
I think if you ask different people, you'd probably get a different response. From my respect, it's governance plus standardization. So who has access to the data? And if we bring things together, we also need to have data standards. There are some great, like with ICAR, data standards for things here, but perhaps we definitely need to develop data standardization better between different devices. And then you have an issue with, that there are differences between different companies' devices. How do we harmonize that data together if they're measuring subtly different things, but at the end of the line, you want to have one metric? That's rather difficult as well.
I see. Okay, thank you very much. Very interesting aspect. Our next presenter, check, is Professor Andres Civils, a professor in rangeland science in New Mexico State University. He specializes in foraging behavior and rangeland raised livestock. He currently leads multidisciplinary teams of scientists who are developing precision systems for beef cattle ranches in the Western USA. The floor is yours.
The title of my presentation is Precision Livestock Farming Systems on Rangelands, Arid and Semi-Arid Rangelands, and I will try to provide perspective on challenges and opportunities of applying such systems to Western beef production endeavors. What I hope to do over the next 15 minutes is talk a little bit initially about the challenges and then jump into the main part of this presentation that has to do with a project funded by the USDA National Institute of Food and Agriculture, through which we are trying to develop and deploy precision technologies on ranches of the Western United States. And I'll talk a bit about the sensors and the hardware that we're using, the communication system, a bit about the data analytics and dashboard end of things. And then I'll end up with a couple of slides, again, on some perspectives of how precision technologies, what role might they play in countries of the developing world. So this slide is to provide context. This is a system where we work in. This is southern New Mexico, the Chihuahuan Desert. This is a hot desert. Precipitation is approximately 220 millimeters a year. The grazing capacity of these rangelands is approximately 200 acres per cow per year. And so the challenges with setting up a system to track animals and infrastructure in real time are major. And so from very basic things as to how to power a gateway, all the way to how do we get the data from the gateway to the cloud, Wi-Fi coverage or cell phone coverage is not available in many areas. And so these are some of the more basic challenges associated with the system and that we're learning about, and I will try to describe later today. We are hoping to deploy precision technologies on 5 different ranches in the Western United States through this project that I mentioned, in ranches here in New Mexico, California, Utah, and South Dakota. If we think of a rangeland animal agriculture system in the context of process engineering and precision livestock farming system where we're monitoring variables in real time and we're manipulating the input, this would be a case of a ranch that does stocker growth, which is common in New Mexico and elsewhere, where the inputs are, of course, forage and water, and the outputs that we would try to measure with these sensors would be behavior or weight or body condition score, try to measure these in real time. And we would then, of course, have to set the targets that would basically trigger a red flag, and that would require management of the inputs to maintain the process at certain levels. What I just explained in the previous slide has to do with challenges measuring these outputs in real time. But added to those, we have, of course, challenges in the types of inputs in these systems. So forage availability is highly variable from season to season and year to year, and is in itself a process with its own inputs and its own outputs and specific sensors to measure those outputs that are often measuring them not in real time. And so adapting precision livestock farming framework to rangelands has these other sorts of challenges as well. And the last one is that automation, that is an important part of these systems in intensive animal agriculture production schemes, is probably difficult to achieve on rangelands. And so what we envision is that these systems eventually, if we are able to make them work, would probably fulfill the role of being a more sophisticated decision support system for a rancher that is making decisions to make their production enterprise more efficient. There are some hypothetical models, proposals of automated systems on rangelands where animals are tracked and where we have automation of feeders, making them available, opening them up or not, and opening gates and closing gates. And so this is a possibility, but perhaps it's still a little bit down the road. We don't see this happening in the immediate future. The Sustainable Southwest Beef Project, so I'm moving into the second part of my presentation. The Sustainable Southwest Beef Project that I mentioned earlier is using LoRaWAN technology to move data from sensors placed on animals and say the rain gauges and water tanks, water troughs to the cloud and to a computer interface to be able to have information again to manage the system. And I'm going to now explain some of the details of the components that we're using and what we're hoping to achieve. So these are the sensors, the gateways, and the network management system that we are using here in New Mexico. And as I mentioned earlier, we plan to use elsewhere. We're using asset trackers as our animal wearable sensors. We're basically placing these trackers on a collar and putting them on cows. So far, with fairly good results. These trackers have GPS loggers, triaxial accelerometers, and the newer generation that we are starting to use right now also are Bluetooth enabled. And so this allows us to collect some fairly valuable data about animal movement and location. The water and rain sensors we're using basically use the same LoRa network to provide us information on rain in remote areas. We're talking fairly large ranches. The ranches where we're testing this right now has 30,000 hectares. And so there are pastures that are fairly far away from the headquarters, and most of our rains are summer thunderstorms that are highly localized. So having information of rainfall that is happening far away from the ranch headquarters is something that is very, very useful in planning grazing on these enterprises. We are using curling LoRa gateways. Basically, what the data we've collected so far, we've collected with this older model. We're now upgrading to a newer model of the gateway that allows us to move the data from the sensors through the gateway to the cloud via either Wi-Fi or 4G technology, and to use both of these systems almost simultaneously. So one is a backup of the other one, and so that is we're still in the process of setting up these new gateways. The data I will show you in a bit were collected with the older model. And the network management, there are many options, of course, to manage the network and to view the data, get the data from the sensors to the cloud and then to the graphic display on the computer, we are using the Actility ThinkPark enterprise framework to do this. So as some of you are probably familiar, the LoRaWAN system allows by movement of data in two directions. So we are basically able to collect data from the sensors to the cloud, but also from the computer through the cloud, configure the sensors in real time. We are able to automate this again. So this is the configuration dashboard for the industrial trackers. Is what we've used so far. We've placed this in a watertight box and on a collar, on a cow, and we're able to configure the mode in which it's working, the frequency at which it collects data, and the kinds of data that it collects. One of the problems that we have and that we've heard other folks that use this technology mention is the fact that each sensor manufacturer have their own graphical interface in the computer. And so when we go on the left-hand side here from our livestock data to the right-hand side to our rainfall and water data, we need to switch between applications. And so one of the things our project is trying to do is to create a single stop dashboard that will display all of these important data for the functioning of a ranch. And here on the animal side of things, you can see some spatially explicit data of the trajectory of these animals on the pasture, and down below some other data that's being collected by the collars, signal strength and temperature and the activity monitor, etc. How we manipulate this data and how we interpret this data is sort of critical of this whole system. So getting the data from the animal and the infrastructure to the cloud and the computer is the first step, and that the hurdles associated with getting this to happen are not minor, but then the major task is making sense of the data. So one of the things that we are doing is using the API of the companies, sensor companies we're working with, is pulling the data from the cloud to our servers and then trying to analyze it in real time. One of the examples of some of the preliminary exercises we've done is to try to calculate the area explored by cows in a day to try to detect important events. In this case, this is the change in area explored by this cow that was basically being tracked during the calving season. And this nadir in the area explored coincides with the calving date for this cow. And of course, we found it in other cows in the herd as well. And so are in the process of finding, as I showed earlier, some of these targets, some of these target values that indicate some important event. Calving, of course, is fairly important for our beef production systems. In the months of between March and June this year, we conducted our first pilot study, and this area here is approximately 6,000 hectares, and the pink points that you see here are geolocation of our cows that were being tracked approximately every half hour. We were doing this with a single gateway, the older generation gateway, that in theory is supposed to cover an area of about 10 kilometers, a radius of about 10 kilometers. We got good coverage up to about five kilometers away from the antenna. And so we're still learning about this, using different sorts of antennas in future, more gateways, but the basics of the system is in place. I'll finish up here in the couple of minutes that I have talking about what I know about initiatives of precision livestock farming in other parts of the world. Just very recently, I was able to be on a similar webinar that was held by the Argentinian and Chilean governments, and was surprised to see the advances in precision technologies that are being considered and being used not only for research, but in production as well. And I think that in the case of both of these countries, they're sort of well on their way to adapt some of the current technology to their systems, and that will probably have similar uses to what we are hoping to do here in the United States. In other other systems in the developing world that are more pastoralist systems, the role of precision technologies will probably be somewhat different in my mind. I've had a chance to do some work in West Africa and Mali, and these are the two slides on the right side of this, the two photographs on the right side of the slide, and a little bit in a part of Mongolia as well. And in both those cases, the main concern appears to be theft of animals. And so using sensors on every animal is a little bit difficult, but there are micro trackers. The same company that we purchase our industrial trackers creates these micro trackers that would be ideal to be used by the herder to sort of see the trajectory of their animals. And I'd be happy to talk more about this if there's time during the Q&A session. So I want to thank you all, and I want to first of all recognize again the USDA NIFA agency that is funding the project that I described in most of this slide. There's a broad variety of institutions that are collaborating on this effort, and you can see their logos there. And the team that is working on the precision ranching project is also a team of animal scientists, engineers, computer scientists. You have it, and their names are there. So thank you so much.
Amazing, very interesting. I really like the presentation and the different technology, different aspect, different countries. Like it very much. There are quite a few questions. The first one was about, from Racheli Gavrieli, do you use Bluetooth for cow-to-cow connection and data transfer?
Yep, thank you for that question. We are beginning to use the industrial trackers that I showed the data from in the slide were an earlier generation that were not Bluetooth enabled, and we are in the process of deploying a new generation of trackers that do have Bluetooth, and we are hoping to look at these animal-to-animal connections. In the past, we've done this using proximity loggers with fairly good results. This, of course, the cost of these trackers is lower, will enable us to put a tracker on every animal. And eventually we would like to also use it, of course, to look at questions of cow-calf pairing as well, if we're able to put some of these on calves. We are, as I mentioned, we're working with a large interdisciplinary team, and we're very fortunate to have Dr. Tony Waterhouse from Scotland's Rural College collaborating with us, who has more experience than we do and is providing valuable input on this. But it appears that the person that asked this question has experience as well, so I would very much welcome picking your brain at some point in time. So thank you.
Yeah, Tony is also on this panel, and he will do the session on the 19th. There are quite a few questions on the social interaction between the sheep and actually in general. I think we should keep it to the last session because we get this question and again from quite a few lecturers. Some technical issue. This micro tracker that you are using in Africa at the end, how long they last on the animal?
So we are not just to clarify, the work we've done in Mali is with store on board GPS collars, and we envision the possibility of setting up LoRaWAN systems and using this micro tracker that has a basically battery life for about a couple of days, but that can be recharged. So when, a lot of the herding in this part of the world is done by youngsters, by children in the school age. These are agro-pastoral systems that we're working in farmers that grow crops, but have, of course, livestock that typically, goats and sheep, that typically range to about 3 to 4 kilometers away from the village and come back every night. And so we think this might be a valuable tool to be able to track where the flock is at a given point in time, and that the father or the person in charge of the household who might be in the village or engaged in other activities could quickly pick up an app on their phone and basically see what's happening. But we are still not there.
How long the battery lasts? 3 months, 1 year, 2 months?
Oh, the micro tracker battery lasts a few days, depending on, of course, on the frequency, but is a rechargeable battery with a USB, so you can basically plug it in and recharge it pretty quickly. The industrial trackers that we're using in New Mexico have, in theory, battery life for a year. We have been able to get 3 months of good data from these trackers, but it sort of depends on what sort of data you're collecting. So we were interested in collecting geolocation data, GPS data, which is more energy thirsty. We have now changed that to collect motion data, accelerometer data, which of course requires less energy and less frequent geolocation data. But going back to your question of the micro trackers, again, it depends on the frequency of the data and what sort of data you're collecting.
I see. There is a good point. The last question you probably can see from Richard Lloyd about the cost effectiveness of the technology. Which of these technology are cost effective at farm level and will therefore significantly contribute to a better welfare and also reduce antibiotic? Two different questions, the cost activities and later on animal welfare and antibiotics. What do you think about?
Yes, the cost is a question we get asked all the time by ranchers. Every time we talk about this is what is the cost per cow? And that is one of the things that our project is hoping to determine. It's difficult for us to say right now, but we're probably in the neighborhood of $40 or $50 per cow per year. But again, these numbers are very, very preliminary. And the second part of the question, the idea, of course, is to be able to detect anomalies in behavior that signal health problems or welfare problems as well, and be able to intervene rapidly. So we are hoping that one of the uses of this sensor network system will be to improve welfare and basically intervene when there are health problems before it's too late right away.
Yeah, I see. Jean Mark and Mark Ruther, you will have to wait for the final Q&A. Just one question that raising up, you said $50 to $40 per cow, but what about sheep and goats? What will be the break even there?
Elon, I couldn't answer that. I don't know. I would be guessing, and my guess would be as good as yours. Yep.
Okay. Okay, so I think we can move to the next one. The other question we can keep to the Q&A session. The next one is my presentation. Sally or Maggie, can you run it?
The British Society of Animal Science, and especially to Claire Thomas for bringing up this issue now, just in time. I think it is the time for the PLF community to move to intensive to extensive systems. I'm speaking on behalf of the Israeli PLF lab, which is belong to the Vulcani Center. It is located in the Institute of Agricultural Engineering and in Neve Yaar. My name is Ilan Alachmi, and here the list of the people in the lab who actually did the work that I presented here today. So I'm speaking on behalf of their projects. There are two main reasons for potential shift from extensive to intensive PLF. One is the technology. Early systems were mainly based on something or sensor on the animal or in the animal. You can see here a list, but there are quite a few more sensors. I listed only those who exist in the Vulcani Center. And what's happened now regarding the technology is that we are moving from one sensor per animal to a single sensor that serves many animals, like a camera or antenna or another sensors that serve many animals. In general, the PLF lab doing both because the idea is to work on the data. It doesn't really matter from where the data came from, as long as you know what to do with the data to get an action list. I will give two examples. One from very intensive system, bolus system, and the second one on the other side of the scale, small ruminants, and all the other projects currently running in the lab are in between these two projects, the very intensive one and the extensive one. So we should start with the intensive one. It is about heat stress, sensing the animal response. The key principle is about the same also for extensive, but the sensors and the concept is different. In this specific case, we are working on cooling sessions. A regular cooling session takes about 45 minutes, where the farmer brings the cows to a shower and wind. And what is done today is we bring the cows based on a predefined time. For example, every 6 hours or every 8 hours, without looking at the animal himself. What Arel it was his MSc student, and it was part of the OptiBarn project. He took a real-time sensor, bolus in this case, and actually looked at the cow temperature, and based on cow temperature, decide if we bring the group to the cooling session or not. The project started with a mathematical model because the standard is vaginal temperature, what you can see here, and we like to work with a Roman bolus, which provide different temperature because there are fermentation process in the rumen, and also every drinking event, as you can see here, make the temperature drop. So we had to work on some mathematical model to adjust our measurement in that we will work with them like in a standard vaginal bolus temperature. So this was the beginning of the project. It was an MSc of a data scientist, Shlomi Goldstein. We did an iterative process every week until we found the best protocol for bringing the cows. And we changed this protocol every week based on the climate change that was predicted for next week, and of course based on the animal response. We also did the crossover and got the same result. Actually, the cows that used to get more cooling systems suffer more when we did the crossover because their heat stress was not built gradually, but once when we shift them from the from the experiment group to the control. When you look at the quantitative result, obviously it reflects what we saw before. By the way, we didn't got any additional milk yield, but we got higher milk fat, we got higher milk protein. They compensate on these two by eating more dry matter, of course. This is also significant. All of this happened because the cow changed their behavior. They changed the timing of visit to the feed. They changed the visit duration. They changed how much kilograms they ate in each meal. They ate more, the sensor-based cooling. Changed their they change every behavior parameters that you look at. They change it. By the way, our Elevate just published his paper from his MSc, so you can read it in Animal. It was just accepted. And further research will be in what happened to the behavior, because as you can see here, this is the time, and this is feed intake per hour. You see there is significant difference between the experimental group, the PLF, and the regular group that were based on regular time. They ate in different amount per hour. They changed their behavior. And also what's happened in the Roman, this is PH Roman, also different. So this is something for further research, and I will be very happy to cooperate on it because I think it is very important. So if you think about new project, I will be happy to. In conclusion, we did this experiment during 2 years. We did it 1 year and repeated next year. We got higher milk fat, higher protein, higher feed consumption. We changed, it happened because they changing the eating behavior, or maybe the other way around. They changed their eating behavior and got higher milk fat and protein, better thermoregulation. Sensor-based cooling found to be effective tool to ease the heat stress. And data for current individual, heat tolerance, phenotyping, biome. It's open a gate for quite a few research that we will be happy. By the way, what you can see here is early type of prototype, very early. Now after 4 or 5 prototypes, we are in a system like this, which is almost commercial. So now we are waiting for a company to bring it to the market. The idea here is that every time a ship of boats to drink water, we take the body weight, which is here. Also, we know which animal it is because we have the high frequency RFID. So we know, and we have the water flow to measure the water index. We know how much water the animal drinks and what the body weight of the animal. It's done automatically without any human. Since there is a problem, I just explained that what you see here is the body weight automatically taking and the water intake that each animal, when it's arrived to this system, the animal just came to drink water, that's all. Here you can see RL who actually put the RFID, and the rest is done automatically. All the rest, and by the way, most of the farms already have RFID on the ear, so everything is done automatically. If you look at the data, for example, weight changes in kilogram, and this is the date. This borrowed from PhD student in the lab, Frat Wilinski. She's a data scientist now. She just finished her PhD. If you look at this individual, it grows rather fast. So how will the farmer will take it for breeding and or earlier marketing? This is an interesting one because here we should have given a lamb. We didn't give it because we like to finish the experiment, but something happened to this animal. This is more interesting because this animal got ill and recovered by itself. And now if it was a regular conference, I would ask you, should we give alarm here or not? Because the animal recovered by itself, so the farmer probably will do nothing with this until there is no need to put medicine when the animal recovered by itself. This is clear cut because here we should have given alarm. See, this animal didn't recover until the end of the experiment. So this example for data, we reach a point of optimal marketing time per individual that we group them together. There's a lot of economical benefit for it, for the optimal marketing time. Tzach Glassar, which was he's a partner in the lab, realized that if he changed the diet and he made a control experiment when he had an alfalfa-based diet, comparing to a wheat diet, the only difference between the diet was the protein, and the animals changed their water intake immediately. They just drink more or less when you change the diet. So you get an early warning notification when something goes wrong with the feed, or if it is on grazing, when you should bring the cows to another field. Very important tool to look at the water in order to know what's happened to the feed. Another practical application is just finding individual. We have a paint, blue or red spray, and every time that or the algorithm or the farmer himself put in the computer that he like to mark specific individual, then the system gives some paint on the back of the animal, and we can find him. So in the morning when the farmer arrives to the system, he saw where are the problems that came from the algorithm, which means blue, or his own reason to separate, which is red. You just see it on the back of the animal. Efrat Wilensky also did a user-friendly interface. This was her PhD. A visualization that by looking at one screen, you can see immediately what happened in the entire herd. You see the different alarm based on the algorithm, and if you touch individual, you can see all the data of this individual in one screen, very easy to use. And we are now working on to make it reliable enough, economic, and we calculate the return on investment on different environment. This is where we need cooperation, because we like to take it to different countries for working on this return on investment, economic reliability, and actually to fit to a regular farm management on validating the system in other countries. So to conclude, if you talk about, we went through only 2 case studies that presented a long path from intensive to extensive system, PLF solution. A shorter answer will be that the technology now fit better for a PLF, for extensive system, because one sensor can serve many animals. And the second reason is the budget, that now more and more European projects, as you can see here, are going into the direction of extensive system. And this is only in my lab. I'm sure in every other lab there are many other projects that went through the same phenomena of financing intensive system at the beginning and now moving to extensive system. Thank you very much for listening. The floor is open now for questions, remarks, ideas, complaints. Now it's the time. Thank you very much.
I'm sorry for the sound, and also the movie jump from time to time. So quite a few slides that or not missing, but or starting only at the beginning. I see one question from John Mark. Which sensor has been used to access the heat stress status of the animal? We used bolus temperature, but there are maybe few more. The animal changed their activities. They arrived to the feed bank when the time is cold, the temperature is lower, and you can measure that. We did it with bolus temperature. A question from Cled Thomas. How PLF sensor can use to estimate greenhouse gas global warming impact on systems. So far you have concentrated on production parameters. If we now move from intensive to extensive system, maybe the next development, the next revolution will be to go individual level for a more polluted or less polluted animal, but we are not there yet, at least from what I know. This will be the next revolution. Now we are still has to move from intensive to extensive system. Maybe at this point, maybe at this point I will move to Kled, that he will chair this session until we move to the Q&A. Kled, are you with us?
Yes, I am. Yeah. Okay. I think there are several kind of issues that have been raised, but please through the chat raise some. I think this is the time that maybe we can raise some general issues, right, rather than individual technology issues. One of the things that was raised, I think, by Tony Waterhouse is this problem of cost. I mean, when you're dealing with very intensive dairy systems, where and intensive poultry and pig systems, etc., the cost may now not be such a major factor, but certainly when you're dealing with small ruminants and especially sheep, the cost of the technology could be a major bar to the take-up, and especially in developing countries, as I think we've heard earlier. So it could be that once we move from, as you say, we're moving from intensive systems into the challenges of extensive, cost of equipment could be a major factor in the uptake of this technology. So I think Tony Waterhouse, you raised this, so I don't know, Tony, if you want to give your views on this.
Yeah, can you hear me okay? Yeah.
Yeah.
Yeah, fine. I think it isn't just a matter of cost, it's actually trying to work out what the benefits are, because that's the issue. It's not simply we're replacing old things. So I think the question will be, what can we do new with this as much as other things? But yeah, I think it's a massive issue when the equipment costs more than the animal. You've got a real problem. It's simple like to asking any of our speakers, how they would deal with looking at, I don't know, samples of animals or using, as Mark Rutter suggested, using a drone as an external camera. Does that actually help us, or do we need to do more of this work with the individual animal as at the core, or do we find ways to look at herds?
Okay. Does anyone else have an insight into how we can overcome that? We can show cost benefits associated with this technology in extensive systems.
Can I come in, Ted?
Yeah, one. Yeah.
In that one, sorry. I ran out of time in my presentation, but the point that Tony makes about the cost is something that we're really going to address in Take Care in the project we've just got, is trying to find a tool that the sheep farmer are happy with, and the cost will definitely come into that. So it might be just a way of starting small and slowly building up with something that the farmer, especially the sheep farmer, will accept, because we know that we are facing with an industry that maybe not used to spend a huge amount of money on an individual animal. But that's definitely something that we will look into.
And
if I could just make a quick comment.
Yeah.
In relation to some of the technology in Australia, industry has actually had analyses done for specific technologies with specific capabilities to look at the costs and benefits, which provides, I suppose, some indication of the sort of pricing that would be needed to make these things viable within industry.
Can I add something?
Yeah.
Over and above, what happened today, and Andrew Dorsey just touched it, we are all connected to the production, to the farmer himself. But along the value chain, there are many people who like to get the data, but today they are not paying for the data. The feed center is very happy to know the body weight of the animal. All the veterinary services like to see if there is something goes wrong. The community themselves, animal welfare. So if we can go in your two projects, Claire, of another business model that not only the farmer pay for the cost of the sensors, but all the users, then I think we have some interesting contribution, which is highly relevant to extensive system, because in intensive system, as it was said before, the animal much more has a higher value. I would like to hear Andrew's opinion about it, about how to make a model that all the users pay not only for the farmers, and also for the...
Yes, no, that's a very good point, and I think yes, we need to talk to all the stakeholders about how this will work, and it may be that there will be some subsidies for using these that could be enacted at a governmental level. If you wanted to use these systems for surveillance activities across for disease or other types of surveillance across a country or region, or for other things like that. There's also, in my mind, the question as to whether, well, it depends what you want to do, but how much can you get from only putting sensors on a subset of the animals? If, for instance, say one of the applications that I know, even though I'm a computer scientist, I guess I know a little bit about now, is the Helminth worm infection. The issue there is that that there are different times, different conditions that this will happen. How do you take all the data, not just the activity or the individual animal data, in order to predict when you should give the anthelmintic treatments? And even that, for instance, has ramifications for policy, because at the moment they're drenching or potentially they're drenching their flocks, and that's causing anthelmintic resistance, which is an issue for the country as a whole. So yeah, I totally agree. It requires, as I say, development with policyholders on the governance of this data and how people can access this data, and the fair use, I guess, and the fair share of the costs of this data.
I think also, and this probably relates more to Europe than other countries. Of course, now the subsidy or the support element is moving away from production to support for environmental benefit.
Yeah.
And it seems to me that certainly in the European context, particularly as most of these extensive systems are in the kind of least favored areas, the ability to use PLF to measure environmental impacts could be a very, very important means of actually getting support to cover the costs. In other words, the cost benefits are not just in production. The cost benefits are in terms of biodiversity and changes in global warming impacts of systems. So this may be the way of attracting funds to support these kind of externalities rather than the conventional production support along the chain that you're thinking of.
I would like to refer to the question from Aline about Brazil, to whom you asked, Andrew, I assume, or Paul?
Sorry, can you explain which question this was?
The one from Alain, what are the main challenge to working with developing country economy like Brazil? Are we working to improve animal in Brazil with technology? Does someone like to take this question? Comparing to what Cled just say about Europe, you have something from the other side of the ocean.
Ilan, I'm not an expert in Brazil, but one thing I can say is that the providers, the LoRaWAN providers we're working with here in the United States tell us that they have big customers in Brazil that are also trying to deploy elements of the PLF system using LoRaWAN and so on and so forth. And the story we heard again is that they are worried with, and these are extensive, we're talking beef systems again, they're worried with theft as well. And so anyhow, that's as much as I know, but I'm not an expert. One thing, if I may, regarding the economics in the Western United States, we've, through our project, have done some surveys, some polling of ranchers in our area, and about a third of them, of the people that the sample size is not humongous, but about a third of the people surveyed indicated that they would consider using animal sensors on their ranch. And the main reasons for not doing it were tied to two things. One was the size of the operation, so the size of the herd, and the other was communication problems in the area where they ranch. And finally, if I may, sorry, I don't want to hog the mic here, Ilan, but in regards to the question of environmental impact, I think that's a very important question. For us here, we see the use of precision technologies as a way to, of course, reduce the costs of ranching, but also the environmental footprint. So in some of our ranches, a manager will drive 30, 40, 50 miles a day within the ranch to check water troughs and to check animals. And we think that being able to monitor remotely in real time would reduce some of that impact, and that those numbers are possibly not trivial. Thanks.
Perhaps I will try to link these two issues. One, what's happening in countries that are not in Europe when the subsidy is less, Brazil, Israel. And the second one, the data. There are quite a few questions here from Mark and from Jan about the data. What I think in the future will be that feed centers, veterinary services, things like these who use the data, I hope they will pay for the systems themselves. For example, for the feed centers who supply feed for the animals, for them to know if the body weight of the sheep and goats in intensive system is going high enough in a good growth rate per specific diet has a lot of value. The same for veterinarians and other things. So if we can reach a point where we can manage all the data, and then you will have a chance that the farmer will be the only one who pay for the system. Like a SaaS, software as a service, and it's already offered in some places here in Israel, mainly by feed centers. Okay. There was a question from Cled at the beginning about the influence of the device, like the walk-through scale, on the animal behavior. You can extend this question to bolus temperature and to quite a few systems when you have to guide the animal to a specific point. And remember that it's all about the individual animal, otherwise it is not PLF. So we like to measure the individual animal in order to manage the entire farm, but we have to monitor the individual.
Yeah, I think I mean, we've seen the potential of, the WOW system, but I was just worried about the downsides, that when you're dealing with free-ranging ruminants, you can actually change, or this is a question really, to what extent are you actually influencing the behaviors of these animals by the placement of the equipment and the methodologies that you're using to attract animals in? They're learning to gain rewards and therefore may alter their behaviors by using these techniques.
Yes.
So is this a downside of what you've shown to be massive potential benefits of walk-on weighing?
Yeah, this was our main reason why we went into water trough attraction point and not guiding the animal to specific place, because we use the same amount of animal per water trough like they do today. I think one trough per 20 animals or so. So we don't change the animal behavior in this specific system. But there is also advantage to a system of mass production. You can bring whole your herd in few hours and get all the weight.
I mean,
just
carry on.
Sorry. Experimentally, if we've got animals within, I suppose, more intensive grazing type studies, we see that particularly as the weather gets hotter, animals will tend to camp because we have a yard attached to the walkover way system. So they will often camp in the warmer times of the day, apart from their peak grazing periods, within the yard. But at other times, it appears to be quite normal. We have had issues in temperate systems using water as an attractant when you have very wet periods and they don't actually need water, of getting the throughput of the animals through the system. So they're just a couple of examples of things that we've struck.
And I just wondered, whether the kind of virtual fencing approach also, again, when you have free-ranging ruminants that, have learned behaviors where, or inherited behaviors or innate behaviors, whatever you want to call them, that move around their ranges to mitigate the effects of temperature, whether that's cold, wet, or very hot, or they move to different parts of the range because basically they have learnt over time, and I don't know how the system is passed on, where the herd moves to these areas where the supply is more plentiful. I mean, as soon as you interrupt those behaviors, you're changing the system using the technologies, aren't you?
That would be something where if you've got the sort of information that, say, Derek Bailey's group has looked at, where they can actually understand where the utilisation of feed, for example, is taking place, or other interactions with the environment, you would start to integrate that into the use of walkover way so that it's actually beneficial. But the other use of virtual fencing. But one of the other uses is actually for exclusion from environmentally sensitive areas. So there's ongoing studies looking at the sort of things you're talking about, whether they're behaving as they would in the more traditional systems, or systems that might use electric fencing or whatever, but also some of those environmental interactions.
Okay. I think we plan to end this in about 5 minutes' time. So, Elan, I think if you have other major issues or general points that have been raised, or anyone else that we've missed out on your general issue, please can you come in now? I mean, just butt in, just turn your sound on and make the point.
Yeah, I think, as I said before, it is now the time for move to extensive system. I don't really know how because different economics, different data, other aspects, but it's definitely what we should do. And I thank the organizer from the BSAS, especially to Maggie and Sally and Cled Thomas, who actually initiate the entire idea, to the presenters, to Paul, to Andrew, to Claire, to Andres. I hope I didn't forget anyone, Tony, of course. And I hope to see you all in the PLF session of the EAP, I think next week or 2 weeks in time. We will continue this discussion in the PLF session in the EAP. So thank you all. And if someone else like to add, please do.
So any other major issues that you want to raise that that we've missed?
It's Mark Rutter here.
Can I add my thanks to everyone that participated? There's the second on the 19th, so at the same time as now. So we look forward to seeing you all then.
Okay. Bye.
Okay, thanks everyone. And that's Sally, Maggie, etc. Can you now close the session, please?
Thank you. Bye.
Oh, thank you for participating.